those are, so I'll pass my papers. Those are things people just turned in. Good afternoon, welcome back to another lecture for Chem 400. Today we are starting Chapter 6. One announcement before we begin today. Office hours this Friday are canceled, but will be rescheduled at a later point. I guess one more announcement. Homework Chapter 5, is due 12:30 by on Wednesday or any time before that, and unfortunately no time later than that. But I do have homework 6. Homework 6. Wow, that's weighty. 9 pages. Well, fortunately, we have 2 weeks to do it in, and so that means not this coming Wednesday, but 2 Wednesdays after that is when it'll be due. So, but it is significant. It is a lot of new topics, but we'll give you some time to do it. Any questions before we get started today? If not, then let's start Chapter 6. Chapter 6 is going to be thermochemistry, energy, 2 main types. Kinetic energy, we've used this abbreviation last chapter, but here it is again, KE. Kinetic energy is energy of motion. And as far as that goes, things have to be moving to have kinetic energy. Gases, of course, moving very fast. Gases have a lot of energy and a lot of kinetic energy as well. The equation that we've talked about already, kinetic energy, Ke equals 1/2 mv squared. And we'll just keep it with no bars on any of them because we're going to actually do a calculation for a specific bullet in this case, of all things. A rifle shoots a 4.25 gram bullet at a velocity of 965 meters per second. What is its kinetic energy in joules? And here's one of the reasons we're doing this is to relate the joule, 1 joule, 1 capital J, to its other units that it's built out of. A joule is a kilogram meter squared per second squared. I think there's probably something, if this were a physics class, to understanding the relationship here. Other than you need, to get energy, one way to get it is mass and the square of velocity. But for us, know that these two are equivalent, and pretty much everything in chemistry is going to be, as far as energy goes, in joules, and specifically kilojoules. A kilojoule is 1,000 joules, as we'll see, because chemical reactions tend to take thousands of joules or kilojoules. Well, let's do this calculation. Kinetic energy equals 1/2 mv squared. Mass has to be in kilograms. V equals velocity in meters per second. Converting 4.25 grams into kilograms, move the decimal point 3 places over, 0.00425. Filling in our 965 meters per second, take that whole quantity squared, plug everything in. And we get 1,979 kilogram meter squared per second squared. And all I want to say right now is that besides 1979, quite a year for me. I was 8 at the time. This is also 1979, 1,979 joules. And I know that's 4 sig figs. We typically give it 3 sig figs. 1.98 times 10 to the third joules is also fine as well. Any questions about this? You know me, I love units, I love canceling units. Part of canceling units, at least in this chapter and moving forward, can be knowing the units that joules are made of. Now, except at absolute zero, all materials have kinetic energy. Absolute zero, another word for that, 0 Kelvin. The kinetic energy of motion of gas particles is called thermal energy. That's a term you'll hear sometimes, thermal energy. That comes from what we talked about last chapter, that the average kinetic energy, that's Ke bar, average kinetic energy is proportional to temperature. That's where the term thermal energy comes from. If you know the temperature, you have an idea about how much kinetic energy these particles have. As far as potential energy, energy of position. Energy of position. Potential energy requires a restoring force, such as gravity. For electrical charges, the restoring force is the electrostatic field. Electrostatic field is a fancy word for the fact that a positive and a negative charge are attracted to each other. And so all I want to do here is draw the fact that these two are attracted. By the electrostatic field, and of course if this were a physics class and not a chemistry class, we would probably get into things like the permittivity and all the relationship. But all we have to know is a few simple things, one of which is that positive and negative charges are attracted to each other. We're going to do a little bit more with that on the next slide. There we go. My question for you, A or B, which is the higher energy configuration? We'll do a show of hands. How many people think A is the higher energy configuration? How many people think B is the higher energy configuration? This is complicated. Let me do today's demonstration for you. It involves pens. Now let me ask you, red or black pen, red. Which is the higher energy configuration? How many people think the red pen? How many people think the black pen? Okay. Now the red pen is farther away from whatever's attracting it. What is attracting it? Really, we consider it the center of the earth, it's gravity. It's attracted towards the floor, certainly, and the floor would stop it, but it would keep going if it could, right? Okay. So, in this situation, the red pen is attracted to the center of the earth, and it is farther away from the black pen, and it is higher energy. Now, by analogy, A or B, which one is the higher energy configuration? How many people think A? How many people think B? It is counterintuitive, and let me tell you in my humble experience why it is counterintuitive. A is the correct answer, but B if we were to talk about what is the force between them, the closer they are, the more force they have. However, we need to say a couple things. One is A, higher energy. A is the higher energy configuration. And we'll draw a little picture over here. And here's my red pen. There's my black pen, and the higher pen has higher energy, and this is potential energy. Is there an equation for potential energy? Again, if this were a physics class, potential energy equals what? Does anybody know? It's not a physics class, so I don't expect you to know. Has higher PE. I bet if I write it, it'll look familiar to some of you. Mass times gravity times height. Does that equation look familiar to some of you? Yeah. And so the higher it is, the more potential energy it has. Any questions about that? But yeah, let's just stop there. Higher pen has, right? Okay. We're going to see that on some level, all of chemistry breaks down into a series of charges that are held in certain positions. And sometimes those will be full charges, like sodium ion and chloride ion, which would be very similar to this. Some of them will be partial charges, specifically when you think of intermolecular forces and dipoles. But in the end, it's all charges, and we just have to figure out what their positions are to find out how much energy there is. Chemical energy usually refers to the energy that is stored in the bonds of molecules. Bonds are going to hold the atoms in a specific position. Bonds hold atoms in specific positions. Boom, you hear the word position, you think potential energy. As those bonds break and are remade, those positions change. We should expect changes in potential energy. Any questions about this? So, a couple levels of understanding. One is, if they're farther apart, know that they have higher energy. Two is to think of this potential energy picture as well, as to how that makes sense. Now the law of conservation of energy. Goes like this: in a non-nuclear process, energy can be neither created nor destroyed. And this is similar actually to the law of conservation of mass. The law of conservation of mass in a non-nuclear process, matter or mass can neither be created nor destroyed. However, what we will see is that potential energy can be converted into kinetic energy and vice versa. Another demonstration, so many demonstrations today. Potential energy. If I let go, will it start moving? That would be kinetic energy. Yep. They're pretty high-tech demonstrations, I know, but try and stick with me. A pen dropped to floor converts potential energy into kinetic energy. That was perfect. Those of you in the front row probably saw that, but I don't know if the back row saw it chipped, right? And that means, so, because my next question is going to be, when I drop it, it stops again. So what happened to that kinetic energy that I had? Heat. And it used it to push this piece across the floor. But in general, heat is the right option. In general, noise, it actually vibrated the molecules on the floor, which then vibrated the molecules. What is noise or sound but the vibration of air particles?
Impact.
Vibration is movement, which is kinetic energy. So we didn't destroy the energy. Where did it go? It just dissipated is a word that we often use. It went to a bunch of other molecules in really small percentages through the impact. And now, thank you. That's pretty. And it still works, which is good. Let's see. Another example, so PE can be converted to kinetic energy. Kinetic energy can be converted into potential energy. And an example of that could be riding a bike up a hill. You're moving and you're raising the potential energy. But we'll leave that one. That's the main one we want to do. Next topic, energy scales are always arbitrary. And this could be a very deep discussion. And I don't know how many layers we'll get into it, but we'll start with this statement. There are no absolute values of energy. We will always measure changes in energy.
Calories.
What's that?
First word. Calories.
Calories will use energy. Let me do an example of this, though. And we'll come back to this equation. Potential energy equals mass times gravity times height. I'll actually define my terms this time. Mass, gravity, and height. They do have to have specific units for us to work out to joules, but we won't be so worried about that. We'll draw our little picture here. Here's my pen. Here's the floor. When I measure height, we could, if we got a ruler in here, we could measure how high this pen is off the floor. Yes?
Yeah.
Now, the floor. We would call that zero. Is that really zero height?
No.
No. What is zero height? The center of the earth could be as where we're... I would suggest there is no zero, because you can always go lower, right? And you can always go higher. So height is really a difference in position. And so if height is a difference in position, then potential energy is really a difference in energy between if the pen was on the ground and if the pen was right here. Okay? So PE is a difference in the energy of the two positions. There's actually more that we can say, but that's the crux of the argument. And no matter what energy you see, it's always a difference. And that will be particularly important in chemistry. For example, the difference we will always be interested in is the difference between the energy of the reactants and the energy of the products. That will always be how we calculate the energy, as a difference. There will be no absolute values. Okay. Now number 2. 2, what goes on this blank? Alicia? Calorie. 1 calorie will raise the temperature 1 gram of water by 1 degree Celsius. The dietary calorie is actually 1 kilocal. An average young adult, whatever that is, expends about 1,800 kcals per day just to stay alive. Now let's compare that to a bullet firing how many so that was joules. That was like 1 or 2 kilojoules. Anyway, we'll relate calories to joules in a few minutes. The blank is a unit of power. The blank that goes there is a watt. Is a unit of power which measures the rate of energy flow in joules per second. Thus the watt hour is a unit of energy. Anyway, these are 2 of the other units that we're going to be talking about a little bit, even as we principally talk about joules. So we wanted to define those.
What's the difference between watt and voltage?
What's the difference between a watt and a voltage? So, let's see. A voltage times a current. So, wait a minute. Volts times amps. I don't know.
Equals watt. Yeah.
Equals watts?
Yeah.
Yeah, okay, thank you. Volts times amps equals watts. Yeah, actually, thank you. It was in there somewhere. That's one of those things where I was like, yeah, that does sound right. Actually. Because I kept getting, well, anyway. There's your answer. Thank you. Heat and work are processes that cannot be stored. We're going to start talking about definition of heat. Heat is a process in which a body acquires or loses energy. The process in which a body acquires or loses energy as a direct consequence of its having a different temperature. As a direct consequence of its having a different temperature. Different temperature than its surroundings. Now, The next question we want to address is, how does heat flow? And I've got my picture here of a campfire. And the pot here, the pot's got water in it. My question for you is, how does the heat from this fire heat up the water? How does it get there? Radiation. Radiation is a term, though, convection, conduction. So, what actually happens? Here's what I'm going to suggest to you, that our picture of heat is related to temperature, and temperature is related to molecular motions. The way that this water heats up is that the fire heats the air molecules. The air molecules bump into the bottom of the pot. When it bumps into the bottom of the pot, that's a solid, right? How do solids have kinetic energy? Do they have kinetic energy?
Yes.
Yes, they do. Everything does that's above 0 Kelvin. Here's kinetic energy of a solid. Here's kinetic energy of a higher temperature solid. But they're held in place by whatever bonds or forces are keeping them there. They can acquire kinetic energy by vibrating in place. So, you heat up the air molecules, they bump into here, that bumping causes more vibrations here. So the pot warms up. And then inside the water, here comes the water molecule. It hits the bottom of the pot, heats up, and eventually the hot ones get down here. Hot water is less dense than cold water, so it rises, creating currents which brings the cooler ones down, which then bump. I am suggesting to you that all heating, all temperature changes occurs by the movement of particles faster to slower. How does heat flow? Faster particles collide with slower particles to transfer kinetic energy and thereby raise temperature. So, I think I just said that well, but I really can't remember what I just said. Hotter molecules collide with colder molecules to transfer kinetic energy and raise their temperature. Hotter molecules collide with colder molecules to transfer kinetic energy and increase temperature. And radiation, that's the name we give for the hotter molecules that are not hitting the pan. You would radiate heat because those warmer molecules would actually hit you and you'd feel that. And convection, that's for the movement of the water. Conduction is you have hotter molecules in the solid phase, and then the handle is colder, and then the energy works its way down the handle in a solid. So they're really all names for the same thing. And as oftentimes happens, when you have multiple names for the same thing, it's because it's important. And but that's all it boils down to, no pun intended. How does heat flow? Hotter molecules. When you get cold because there are colder molecules bumping into you and you're giving them heat. That's all it is. So, any questions about this? So that's heat. A transfer of energy by any other means than heat is called work. There are two types of work: chemistry and all other. No, that's homework. It's a different kind of work. Two types of work: mechanical work and electrical work. For mechanical work, I've got a little picture of it here. Work. Will be a force times a distance. Electrical work will be moving a charge through a potential. Where potential is another word for voltage. And we're actually going to do some calculations of mechanical work in this class coming up. Work can be completely converted into heat. Heat cannot be completely converted into work. I apologize, there's a typo there. Work. Now, contrary to Chapter 5, in Chapter 5 we did all the calculations first, and then we talked about theory. Here we're basically building up some theory of what heat is, what energy is, what types of energy, and then we'll do calculations. Slide number 8, number 2, a thermodynamic view of the world. There are system, and there is a system, and there are the surroundings. The system is the part of the world in which we are directing our attention. Surroundings, everything else. 75% of the time for chemistry, the reaction, where I've abbreviated reaction RxN, the reaction is the system, and you'll be given the reaction. 25% of the time, the system is a material. A material. And I'll say more about that in a slide or two. Next, a closed system, and these are definitions, is a system in which matter cannot enter or leave. And an isolated system is a system in which matter and energy cannot enter or leave. And it's not a huge deal, but most of the systems we will be using in our closed systems where matter cannot enter. Examples of system and surroundings. Question, Bodhi. Let's do these two examples, and then we can talk. Go back to closed versus open systems. Okay. Examples of system and surroundings: the dissolving of 10 grams of ammonium nitrate in water. The system will be the reaction. And it's a dissolving reaction. We've written dissolving reactions. Take whatever's dissolving, in this case ammonium nitrate. Put it in the solid phase, or whatever phase you think it is on the reactant side. The product side will be aqueous species. This particular one, since it is an ionic compound that does dissolve, it is a strong electrolyte. It will break up 100% into ions. We have ammonium, which will be aqueous. We have nitrate, which will be aqueous. Surroundings, everything else. Do you remember dissolving reactions? Do you see? So the only way that water enters into this is through the aqueous phase. Meaning, and do you remember what aqueous means? Do you remember the hydration shell? In this case, it's a hydration shell of water molecules. That's what aqueous means. A pen is held 2 meters above the floor system. I said 25% of the time the system is a material. This time the pen is the system. Let me just write out surroundings. Well, perhaps you'll start to see a pattern here. The surroundings here are everything else. Yes, Bodhi, question?
So when you say everything else, you mean like the water molecules, the container, it's in air above the container, that would all be the surroundings?
Everything else is the surroundings. And it gets a little hard to think about when you think about that we're just including in the system the water molecules in the hydration shell, if you will, and not the rest of the water. And what we will see, one thing at least, maybe two things. One thing, it is very important how you define the system and the surroundings. Two, I will always define the system and the surroundings for you. So this is one of those topics that's a pretty deep topic that we will skirt. Like, know that it's there, but we will, like, when I give you a reaction, the reaction is the system. And that's what you will focus on. Now, you were also asking about closed versus open system. A closed system would be the stuff that you have here, and the stuff, like, there's no, basically, matter cannot enter or leave. You're always, whatever's on one side is also on the other, which technically means that the water molecules in the aqueous phase are being considered here. It's hard to think about, but it's true. And the example of an open system, well, it turns out that open systems are very hard to calculate anything for. So we, yes, matter could enter or leave, but actually keeping track of energy in that case will be very hard. So they're basically not used, and certainly not used by me. Which may not be a good answer, but it may be sufficient for now. Yeah.
And then,
yeah.
and then assuming the second example, this will remain the case until and unless the pencil hits the floor. then the floor becomes part of the system.
Actually, so it'll just be the pen, and I wonder if it'll break again. Nope. In this case, what we will see is that the system, we will calculate the energy for the system, and any changes in the energy of the system, that energy goes to the surroundings. So when I talk about this pen, and it drops and it creates noise, that is it giving off energy to the surroundings. Yeah, Jason?
Since the system's just the pen, there wouldn't be any potential energy, would there?
No, so wouldn't there be any potential energy? Well, if I just look at the potential energy of this pen, I can calculate that. I don't need the center of the earth, right? And it's tricky, I know, but if I said, what's the potential energy of this pen? You could go PE equals mgh, and all I need to know are properties of this pen. Its height and its mass. And the gravity would play the role of whatever attractive force there is. So good question, but I think in this case, we can just call it the pen. But they're tricky, and so you will find that we will keep it very simple. Basically, that's the answer. And so perhaps you are wondering why I am wasting your time. Or more importantly, why am I telling you about this? It is important how we define the problem. And if you want to talk more about it, I'm always happy to, but I will always define the problem for you specifically. And where we're going with this is, for this reaction, one of the reasons we need system and surroundings is when there's a change in energy, we will know that that energy, if it is given off by this reaction, goes to the surroundings. And if the reaction takes in energy, which this reaction does, it comes from the surroundings. And in fact, let's see. I just thought of this. Let's see if this works. No, it didn't. I'm trying again. Ow! See, it transferred energy to my foot, which was part of the surroundings. And I pretended that it hurt. I'm the surroundings, because I'm not the pen. Anyway, so that's what we're going to say. Any other questions right now? Okay. Yeah, it's like, what would you even want? Anyway, we're believe me, we're going someplace. I don't know where it is. Couple more definitions: state functions or state properties. Typically, the term I use is state function. A state function is a function whose value is independent of the path from initial to final state. Sort of says that right there. Here's the path and height or altitude. Is a state function. And I've got two pictures here. I've got path A. In path A, the person walking it walks up zigzag style. And in path B, they go straight up. And in both cases, they go from 0 to 10,000 feet. And in both cases, the altitude or the height is the same, independent of path. Path A or path B? which one do you think the person took more energy to do, or let's say this, did more work?
Safe?
Have you ever hiked the Grand Canyon? Have you ever done a hike where you were going this is always the method I do, by the way. And you see somebody going like this. Could be the same. Could they be different? They're not necessarily the same, let's say. I mean, it depends. Like, I could be walking up this, and then they could be like lifting themselves up like that. And I'm not sure that would be lower, less, or more energy. But it is not necessarily the same. So, and here's where I'm trying to get with this. Values of state functions. Pressure, volume, and temperature are going to be state functions that we've already run into. And you can think of them in terms of, like, we've already got equations that involve those. And so we don't talk about the anything except the beginning and the ending point. And the two non-state functions are going to be work and heat. Not state functions.
Why state function?
Why state function? So state function, so I guess where we're going with this and why we're doing this is that some things that you do, if you know the beginning point and the ending point, you can calculate their changes. Some things you cannot. And the two things that we will get to are work and heat. And so if you've ever driven a car, and you've driven, like I have, I'll personalize it a little bit. I have a Ford Focus. And my wife has a Dodge Ram 1500. And we drive from here to San Francisco. Which one's going to take more work to move? Or which one's going to get better gas? Which one's going to take more work to move from here to there?
The larger car.
The larger car. Now let's suppose that you took the Dodge Ram engine and you put it in the Ford Focus. Be quite a car. Would their amount of work it takes to get there be the same or different?
Same.
It would still be different. And that's because and you could think of it as how much gas would it take. You could certainly say that the Ford Focus with the truck engine could get there faster, but it would still be less efficient. And that's where we're going. Like we're working on it. Again, no pun intended. But we're going to get there. So the only things we can calculate in chemistry class are going to involve state functions. So anything I ask you to do a calculation for, it's a state function. We're going to do a couple work and heat calculations just to show you that they're not the same. But then we come back to state functions. Couple other terms, and we're almost done. We're almost ready to talk about calculations. Internal energy has the symbol U. It is the sum of the potential and kinetic energy of all particles in the system. Absolute values of U cannot be determined. Only changes in U, delta U, can be determined. There are only two ways to change delta U. So this says delta U, that's the Greek uppercase letter delta, it's a triangle. is the change in internal energy. And it is Q plus W. Where the change in the heat of the system is Q, that's lowercase letter Q. And Q, which is heat, is not a state function. And Q, when Q is greater than 0, heat enters the system. Q less than 0, heat exits the system. The change in the work of the system, that's going to be W. W, not a state function. We're going to make the same two statements about work down here. For work greater than 0, work enters the system. And for work less than 0, work exits the system. Now there's one type of work that we will actually calculate in this class. It's called pressure volume work. That is the pressure volume work of an expanding gas. And from a previous slide, I gave you the definition that one way you can find the work is that work equals a force times a distance. And that was almost entirely correct. In order to get it correct, and in order for it to work with this convention, I have to add a minus sign. So please add a minus sign. And if you remember back to when we first talked about percent error, and we said that the sign of the error mattered, here's another case where the sign matters, because the sign will tell you whether work is entering the system or work is exiting the system, as we will say. The picture that we've got here is we've got a gas with P1, V1, and T1 at an initial state. That gas expands to P2, V2, and T2, and when it expands, the gas does work because it lifts this weight. So the gas does work because it lifts this weight. Because that's the first thing we have to prove, is that we're actually doing work, and if you're lifting weights, hopefully we can say that that's true. All right. And the distance that it lifted this weight is D right here. We're going to put that in right there in a second. Except that I'm going to call this delta x. The change in position is delta x. And the bottom of the piston has an area A. Well, so I'm going to call my F as my force, and my distance is delta x, where my delta x is right here. And I'm going to multiply both sides by the area A. And since A over A is just 1, it's like I'm multiplying it times 1, which is fine. I'm going to take this A over here to get minus F over A. And I'm going to keep the other A over there. Now what we're doing is actually what's called a little mini derivation. We're going to take an equation from physics, an equation perhaps we've seen before, that work equals force times distance with a minus sign in it. We're going to convert it into what we're interested in. Way back at the beginning of the gases chapter, I defined pressure as force per area. So force per area equals pressure. So I'm keeping my minus sign. Force per area equals pressure. So that's what I've got right there. And delta x, which is in this direction, times the area of this bottom of this container, well, delta x times A, that's volume. And the delta comes in, meaning it's a change in volume that is due to the change in x of the height. And so, this is the equation we want, derived from, let's say, physics. The work of an expanding gas is the pressure times the change in volume. The work of an expanding gas is pressure times change in volume. And there is one assumption to this, and the assumption is that pressure is constant during the process. Pressure is constant. Now a couple of examples, and the first two examples are going to be examples that use this equation, then we'll get back to calculating work. And the problem goes like this. If the burning of the fuel in a potato cannon performs 855 joules of work on the potato and produces 1422 joules of heat, what is delta U for the burning of the fuel? And for this particular one, since we're calculating delta U, that's the change in internal energy. And it says if the burning of the fuel in a potato cannon performs first off, what is delta U for the burning of the fuel? Burning of the fuel is our system. Is burning a reaction that we're familiar with? It is. So it is a reaction and the system is a reaction. Okay. Performs 855 joules of work on the potato, so the burning is doing work on something. That means that work is less than 0 and work is the negative 855 joules. And produces or gives off 1422 joules of heat. The heat is less than 0 because the reaction is producing or giving off negative 1422 joules. Question, what is delta U for the burning of the fuel? Ooh. I'll list my Q first. It should be minus 1422. Plus a negative 855. I'm keeping my plus to keep the plus there, similar. And I get minus 2277. And there's a companion problem here, which you'll find on the Chem 400 website. And I'm going to keep this stuff up over here, even though I'm just going to rotate this slide now. Because now we're going to do pressure volume work. It says, find the amount of work on done on the surroundings. Sorry, I moved on pretty quickly there. Were there any questions about that? I can see that. Okay. Says, find the amount of work done on the surroundings when 1 liter of an ideal gas, initially at a pressure of 10 atmospheres, is allowed to expand at constant temperature to 10 liters by A, B, C. So by 3 different methods. And let's start with A. It says, when 1 liter of an ideal gas, initially at a pressure of 10 atmospheres, I'm going to call those P1 and V1, is allowed to expand at constant temperature to 10 liters. That shouldn't say atmosphere, should it? We don't know P2. We're going to assume that temperature is constant, that this is in a container, so moles are constant. So we have an equation that says P1 V1 equals P2 V2. We can solve for P2. The math's not too bad in this one. What do you think P2 will be?
100.
Just 1. 10 times 1 for the P1 V1 P1 times V1 divided by V2 should get 1 hemisphere. Now, that's the calculation that we do to find out what our final atmospheres are, our final pressure. To find the work done as that gas expands from 1 liter to 10 liters, it is always P2 that you put here, the final pressure, because of the assumption that P is constant. And the way in which you can think of this is you have 2 weights here. You remove one of them instantly. Not so good at snapping with that hand. And then this rises. Alicia, question?
When you compress gas, you increase its kinetic energy. Does the temperature go up as well or not?
Good question. When you compress a gas,
Why doesn't it?
Does the temperature go down because it expels heat?
let's say this. The question as to what happens with temperature and therefore kinetic energy, because they're related, right?
Why does it not go up?
Is does it go up or not? And the first answer is it could, it doesn't have to. But we're going to expand. So when we expand the volume, well, it says something has to change. But it doesn't have to be temperature. And if it's not temperature, it's not the kinetic energy.
Okay.
Right? If we wanted to increase the pressure without changing the volume, we might want to increase temperature. But in this particular case, it is relatively easy to do to keep temperature constant. Does that answer your question?
What's the last sentence?
Say that again?
What was the last sentence?
Oh, so it is relatively easy to keep temperature constant when we do this process. This process is exactly what we're doing. We are essentially, the process is remove a weight, the pressure goes immediately to the final pressure, and then the piston rises. You okay, Stephen? Is that, yeah, any other questions? So, first answer, it's always the first level of understanding, it's always the final pressure. Second level of understanding, because it's like we're instantly removing this weight and allowing the process to occur at the final pressure. And now we have our change in volume. And it's at this point that I will tell you that any time you see a delta symbol for a change, the delta is always final state minus initial state. Our final state is V2. And actually, I'm actually going to write V final minus V initial to drive this point home. Always, 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 final minus initial. When we see delta T shortly, it will be final temperature minus initial temperature. When we calculate different things, it'll always be products minus reactants. Why? Because products are the final state. And that is what all scientists have agreed upon. All sane scientists. You try and get 100 scientists to agree on anything, even something that's ridiculously clear, in my humble opinion. And you'll still only get 97 of them to agree. Anywho, so now we have an equation we can work with. We will have P2, which is 1 atmosphere, so it's minus 1 atmosphere. Our V2 is 10 liters, our V1 is 1 liter. Subtract this out, we get 9 liters, 1 atmosphere. Our answer for work is minus 9 liter atmospheres. Yes, that's an energy unit. However, it's not an energy unit we're particularly used to, and that's why I give you the, on the previous slides, 1 liter atmosphere equals 101.325 joules. This one asks for, it doesn't actually ask for the number of joules, but on your homework for chapter 6 coming up, all the answers are in joules for the amount of energy, and so we'll go ahead and do this step by. And we get 911 joules. Oh, sorry, minus 911 joules. Do not, Bill, that instructor, do not drop your minus. Questions about this? Because that's only A. For B, B will take up less space. B is going to be the two-step process. In B, we're going to take reducing P first to 5 atmospheres and then to 1 atmosphere. Our initial state is still the same. Except now we're going to have an intermediate state. Our final state is still the same. Should say P1, V1 there. Let's fix that. Now our initial state is the same. Our final state will still be the same. And now for our in-between state, it says reducing pressure first to 5 atmospheres. And what does our volume have to be here? 2 liters. So I'm going to call this work for step going from 1 to 2. Sorry, from here to here.
What's it, W12?
That's from 1 to 2. I don't know if this is any clearer. 1 arrow to. Because what I'm doing is I'm breaking this process in A into 2 smaller steps. And for the first part, I get minus 5 liter atmospheres. Oh. For the second step, I have one atmosphere, which is the pressure in step 3. And the change in volume, 10 minus 2. And I get minus 8 liter atmospheres. The amount of work I get out of the system is negative 13 liter atmospheres, which is minus 1317 joules. And some notes in the time that we have left, which is about 4 minutes. One, those amounts of work are different because work is not a state function. The amount of work that the expansion of a gas does depends on the path that it takes. So if we were to imagine this process as having 2 weights, and then the final is having 1, if we could take off half of this weight at a time and do 2 steps, that's sort of what we're imagining here. Next part, B, smaller steps produce more energy. And there is a direct analogy between if you take and drive a car from here to San Francisco, and you use lots of little tiny cylinders in your car, breaking the work up into smaller jobs, you will be able to do it and get more work out for the same process. Versus if you take a V12 or a V8 engine, and those have big cylinders, those would be big processes, and it will be less efficient. You will get less work out of the bigger steps. And again, it's not a perfect analogy because there's bigger cars and smaller cars there, but the message is the same. If you break work into smaller steps, you will create more work from it.
So it's like driving your car in a first gear.
It's like driving a car in first gear.
Fast.
That has the most power. I don't have to think about how gears. That's something
Maybe.
related. Yes, I'm not sure it's the same thing. I think it's probably pretty close.
Or just taking smaller steps.
Yes. The gear ratio definitely matters. Anyway, so there's 2 conclusions of this. 1, the work is different. That's because work is not a state function. 2, the smaller the steps that you do, the more work you will get out of a system. This is the system giving off more work, even though it has the same starting and ending points. And that seems like a very appropriate place to stop, even though I still have a minute left. Any questions about that, I guess, for that last minute? Leo?
So if one gives off more work, that means it's giving off more energy, right? Like, so my question is, where is that coming from for the second one? Like,
Where is the more work coming from?
Yeah.
The more work is coming from doing those same job in smaller increments. So what you can imagine is if you had one big piston in your engine and went boom as the burning reaction happened, or then you had 3 or 4 smaller pistons that all went boom, 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 you would get the same amount of reaction, but you would be able to, doing it in smaller steps, allows the reaction to create more work. I know, it's like magic, isn't it?
Yeah.
Can you imagine? But it's like magic in every aspect except one, and that this is actually true. But think about it, because there are applications to it, and specifically to engineering. All right, I think we're done there. Happy to take any more questions.